So welcome everyone to the Air-Sea Fluxus from Space webinar series. This is the second in the new series, and we're fortunate to have Christine Gommenginger today, who's going to talk about SeaSTAR, the Earth Explorer 11 mission candidate that is about to go through a big proposal review. So take it away, Christine.
Thank you very much, Sarah, and thanks for having me in this series to try and raise awareness about SeaSTAR, which is this mission concept that we are putting forward to the European Space Agency Earth Explorer 11 program. And now I will try and explain a little bit about the process and where we're at as well as give you an overview of what the mission is aiming to do. So I'm Christine Gommenginger, and I am the PI for SeaSTAR. I work at the National Oceanography Centre in the UK. And this is done on the back of work of a very, very large number of people, which is why I couldn't fit this or everybody on the slide, but I do have a slide later where you can see the sort of breadth of people who are involved in this project. So this is about the, just a quick word about the European Space Agency Earth Explorers program. You will have heard of missions like GOES and SMOS, Cryosat, etc. These are all Earth Explorer missions that have, gone through this process in the past. The most recent approved mission, of course, is Harmony, which we will hear about in this series later on. From Paco Lopez Deca, who's the PI for that. And Harmony was approved in June 2022 as for the Earth Explorer 10 program. So we are concerned with Earth Explorer 11, so it's the 11th call in this series. And we are currently at the stage where essentially we have 4 candidate missions. And of course, SeaSTAR is the one that we're going to be talking about. The other 3 are atmospheric missions. I will not talk about those, mainly because I don't know very much about them. Just really a few words about the context of the Earth Explorers. These are the sort of 7 assessment criteria against which the missions are going to be judged. And the emphasis is very much on scientific excellence and technological innovation, but increasingly with a look at societal benefits as well. There are some really important criteria in there to do with usefulness. You have to demonstrate that your mission is delivering a need, addressing a science need, something that we cannot do currently, be it from space or indeed from any other means. So uniqueness is a really important, very important aspect here. And of course, complementarity. This has got to fit within the context of everything else that is happening. And I'm saying I'm highlighting those because I will be talking a little bit more about this later on when we talk about complementarity with Harmony, for example. So this is the front cover of the proposal that I submitted all this time ago, December 2020. Seems like such a long time ago. And the focus then was very much was always about this small scale ocean dynamics, and on the back of these satellite images from optical sensors that we see, where we see all these incredible structure in the ocean at those very small scales, but have actually it's very difficult to know what the dynamics are associated with these, because these are so small and so difficult to observe. So just give you a ballpark figure, for those of you who are in the game of putting these proposals for missions in, it's a relatively large mission by ESA standards. So it's 450 million euros. This is actually relatively small by NASA standards. But for ESA, this is one of their sort of larger type mission that they will launch, although 250 million for the payload is not actually all that much when we're talking about very innovative technology. So 16 proposals were submitted, and as I said, 4 were selected to enter what's known as phase 0, and SeaSTAR has therefore, we are just completing this phase 0 now. I said there was a huge community of people working on this on this concept. There is, of course, many years ago, I led this paper to the Oceanobs conference in 2019, which is here on the right, with a very large number of people. Some of you are online today who were already supportive of this idea of this concept. More recently, now we have, as we are in phase 0, we have, of course, a mission advisory group, which is the box in the middle there, where we had 12 or so people. You will see some familiar names there, people who are supporting us by advising us how to develop the mission. And then we have all the ESA activities, like the airborne team, which I will show some results from that later on. And various other sort of activities associated with the mission. So the process, so we are in phase 0 at the moment, coming to the end of that now. And what the really important point is that we have this user consultation meeting in Bucharest, in Romania, on the 10th and 11th of October, when the decision will be made about which 2 missions go forward to phase A. So, of course, we don't know which ones will be selected, but 2 will be selected and 2 will be not selected. And the 2 that go forward will then undergo another 2 years or so, 18 months or so of studies before we have another user consultation meeting in the summer of 2025, when they will decide which one of those 2 will make it to implementation. So the process is still quite fraught. There's still 2 big hurdles on the way to launch through these 2 user consultation meetings. But of course, once the decision is made in summer 2025, that mission is then approved and can no longer be stopped. So that's slightly different from the way other space agencies are dealing with their new missions. So what immediately of immediate concern is this user consultation meeting in Bucharest. So the details are there. Please attend if you can. I believe ESA will make it possible to participate remotely as well. I know that the time difference will probably not be great for some of you, but if you can attend, it's really important that the science community expresses itself and shows support for the missions that they are interested in. We are the only non-atmosphere candidate in those 4 at this stage. So I'm really counting on the ocean community to come out in force to express their support for SeaSTAR. Okay, so this is a little bit of a preview of some of the material that will be presented at the user consultation meeting. So the format of the meeting will be 2 days of presentation. So each mission has half a day or so to make a presentation about their science case, the motivation, and what they measure, their performance, etc., etc. And then at the end of that, the selection committee goes into a sort of closed chamber and makes a decision about which ones go forward. So there's a lot of kind of material being put together to document this kind of important event, and this is one of those key visuals. So each mission will have something like this. So in the case of SeaSTAR, it is trying to capture really the essence of the mission. So the globe, actually, you will notice the sort of the golden rim around the ocean. So our focus is not on the global ocean, on the open ocean, but very much on the margin of the ocean. So coastal zone, marginal ice zones, and shelf seas. And the reasons for this is, as I had already shown or mentioned earlier, is this interest in those very small scales, at scales below 10 kilometers, that we can see so clearly in high resolution sea surface temperature and ocean color, as for example here in the Baltic Sea. So we, like as I mentioned, we have actually 3 large domains of interest. So all the ocean margins, and they are broadly divided into these 3 categories: coastal, shell seas, and marginal ice zones. So for the coastal, it's a it's a very, very broad mission. We have very many kind of interests. The focus is really on the fast evolving processes. So, for example, in the top panel there for coastal, we see a sequence of chlorophyll concentration on 4 successive days. I think this is over Patagonia at the river. You have a sort of river plume coming out, hence the colors, very heavy sort of sediment loads. And then, as you can, if you can't, I didn't put in a movie, but you could have a movie and you can see these features evolving day to day in a way we can see in sequences of ocean color images, but we can't actually get the information at that sort of frequency currently about the dynamics. So we're interested in this, all these fast evolving processes that affect chlorophyll and sediments and generally the transport of things in the coastal zone and also from the coast towards the open ocean. We're interested in air sea fluxes in the coastal seas. How do they differ from those in the open ocean? How do they affect processes, biogeochemical processes like carbon cycling and so on? More mundanely, perhaps, of course, coastal seas, are dominated by current wave wind interactions, and that is a source of many coastal hazards. So we're also very interested in those. Marine renewables is a big push in Europe at the moment for development of large-scale wind energy farms, particularly in the North Sea, with all the information gaps that they have at those scales to actually understand the resources, manage the deployment of those installations and assess the impacts, which are already kind of being seen particularly on coastlines and on water quality. So I won't go through all of those, but shelf seas, similarly, we have a number of themes ranging from the very sort of popular, fashionable sorts of sub-mesoscale kind of problems which have arisen, thanks to all the interest around the SWOT missions, for example. So we are offering to complement what a wide swath altimeter would be doing by providing measurements of currents and winds, not sea surface height. But we're interested in the small scale processes also, for example, affecting buoyancy fluxes, for example, in Sea, where some of the buoyancy fluxes are driven by very fast and very small scale kind of wind effects in those regions. And then finally, marginal ice zones, both interested in the interactions between currents and winds and waves and ice at the edge and how that affects the evolution of ice on those very short timescales. And then finally, the Southern Ocean, of course, which has been in the news very much in recent weeks, and how the ice is changing, seems to be showing greater sensitivity to extremes. So sorry, I spent far too long on this, but really just the report has got a very large section on elaborating the case for in every one of those cases, or every one of those topics. So as you can see, it's a very, very broad topic ranging from biophysical interactions to coastal hazards to interactions at the ice edge. From this, how we summarize this is through these 3 science goals to try and see what we are actually trying to achieve with this mission. Is really about understanding the role of these fast evolving small scale dynamics on exchanges between land, cryosphere, atmosphere, biosphere, and the deep ocean. So this is kind of the top level requirement, a top level goal that will drive the requirements for the mission, is to be able to resolve those very, very rapidly changing small scale processes. The second goal is to determine the ocean circulation and dominant transport pathway in the global ocean margin, so in the global coastal ocean, shelf seas, and marginal ice zones, which is surprisingly badly observed. It's particularly surprising that the coastal zone seems to be so poorly coverage there seems to be so patchy, which is a real surprise, really, when you start to look at it, just how little information it is about the coastal ocean. And then finally, really to try and understand, put all this in perspective, and try to reduce uncertainties about the contributions of these ocean margins to the global climate system. We kind of make assumptions at the moment that the coastal shelves and marginal ice zone essentially just operate the same as the open ocean, and that is really not correct in some cases. So this is kind of some of the high level objectives of the mission. And one of the important things in this process is really to show traceability. So you once you set your science goals, you have to try and articulate it in terms of what do we need in terms of observations, in terms of sampling, in terms of coverage, and then you end up with a series of observational requirements. So in our particular case, our interest in these fast evolving small scale dynamics means that we want to measure currents, but with a very high level or very low level of uncertainty, and at very fine resolution. So we're aiming for a resolution of 1/1 square kilometer, so 1 kilometer, and an RMS error that is less than 0.1 meter per second, which is it is very challenging. It is, you know, very really pushing the boundaries of what is possible with this from space. The focus on ocean margins means that we have to measure all coastal shelves and marginal ice zones, of course. Our interest in the dynamics, and particularly these a lot of the sort of theoretical ideas that are currently being discussed about energy cascades and what happens between 100 kilometers and below, means that we really want to be able to observe the whole of that, all the scales from 1 kilometer to 100 kilometers, essentially, which is driving this need for a continuous swath of at least 100 kilometers, ideally even more. And then finally, because we see from these satellite images of ocean color and so on, we see how fast these processes are evolving. We do need to have a sort of daily or even sub-daily, if we can, which is a big ask, because that is not a straightforward thing to do from space, but it is a challenge which we have decided to tackle here. One of the very important requirements, as I have already said, these are essential requirements for the mission, and they're really encapsulating SeaSTAR, is this combination of very fine resolution of 1 kilometer or finer, and an error of the order of 0.1 meter per second or less. The requirement is particularly stringent on currents. That is the challenging one. Of course, we do want to measure winds and waves as well. And winds are similarly going to be measured at the same sort of resolution. But the challenge of measuring winds at this kind of resolution is much less than it is for currents. So I'm not going to talk very much about the ocean surface wind retrieval, not because it's not important, but because it's less of a challenge than it is to do the currents. And also I'm a little biased because I'm an oceanographer. So you have seen this already in the original image earlier in gold. Now it's in red, but this is essentially where we will measure. This is the phase 0, what we call the COSMIS, the coastal mask, coastal shelf seas and marginal ice zone mask, as it stands at the moment. And as you see, it is the global ocean margins all around land and ice. We've also kept some provision to be able to take some measurements in open ocean at some special sites of interest, because there will always be some activities or some phenomena happening somewhere in the open ocean. So these are just randomly scattered here, completely at random. They could be anywhere. And we are, in fact, retaining the ability to also move them around during the mission. So they're not fixed forever. This can evolve. And like I said, this is phase 0, coastal mask at phase 0. So this is almost certainly going to evolve if we move to the next phase. What is perhaps more novel, the more novel part of the mission is this choice to go for one-day revisit, and also with sub-daily in some places. And we are in a very we have an orbit altitude, which gives us a very nice sweet spot where we can very easily, with very little expense, move between orbits. So we can achieve a one-day exact repeat, like SWAT has been doing during its Calval phase, for as long as we wish. Of course, that really is a limit how many tracks you can have. You have around 15 tracks or revolutions per day. But by just changing the altitude ever so slightly, we can move into a drifting orbit, again with a one-day revisit, but then it's sort of the orbit kind of gradually drifts and moves out of the area, and then revisits, comes back to the same spot 91 days later, and there's another drifting orbit as well. The same is true, but with a repeat of 271 days. So this gives us a very nice balance between being able to look at the fast processes over extended time, but also over short time and many different sites, and also looking at different sites in different seasons. So that's what the plots on the left, on the right are showing. Apologies. So the top right shows the number of consecutive days that you can see, you can observe with the 271 day. And then the bottom plot, the sort of stripy plot, really shows the minimum revisit time that you have at the crossovers. So at the crossovers in those orbits, we are able to achieve a sub-daily sampling. So in some cases at lower latitude, it'll be sort of 12 hours. So at higher latitude, it'll be several times a day at different times of the day, which will be very interesting for some processes to do with, for example, diurnal warming and so on. A quick word for those who have not heard of SeaSTAR before. This is the measuring principle that we use and that we have to use to achieve the performance we want to achieve. It is highly squinty, the long track interferometry. So a long track interferometry means you're looking at the phase difference between two radar images taken at a very short interval in time. So you look at the same spot on the Earth, very short time difference in your long track, and that gives you a measure of the velocity in the line of sight that you're looking at. So here we're doing this in two directions. So we have a pair of antennas looking forward 45 degrees and a pair of antenna looking backward 45 degrees. So in the first instance, you get the interferometric pair getting the one component, and then the second pair gets the second component of the ocean motion. And then we've added a third antenna, a third look in the broadside. That's the sort of little green arrow in the middle that gives us a third azimuth direction. And with three azimuth direction, we essentially return into a sort of scatterometry type configuration, but with a very fine resolution. And this allows us to retrieve both the wind and the current vectors simultaneously, without making any assumptions about either the wind or the current. So that is, in a nutshell, really what differentiates us from many other systems, is particularly this azimuth diversity, which, this quasi-orthogonal orthogonality between the two views that we have. So we get a lot of data from this type of system. We get backscatter and a Doppler measurement of phase difference in the forward direction, in the backward direction, and on the broadside. And you basically put all this in this equation at the top, which is the cost function that we use to minimize the difference between what we observe, radar backscatter, or the surface velocity that we measure, and the model, which a parameterization of a dependence of those observables on winds and currents. And by doing this, we have tested this with numerical simulations. So on the left-hand side, I'm showing really a summary result of the performance that we achieve for uniform conditions. In this case, we have wind speed of 5 meters per second. As you can see, a velocity of 0.6 meters per second. Anyway, the details are not that important, but really just to show the sort of RMS error that we achieve with the instrument that we propose, that are well within the requirements that we have set for 0.1 meter per second, for example, on the current magnitude. On the right-hand side, we have a figure with 4 panels where we applied the inversion, retrieval inversion, to some simulated data for some realistic fields. So here you can see the top left sub-panel is the original input from a model, from a high resolution model, 1 kilometer resolution model for currents and winds. I think it may well be in the California coastal current, if I recall. And then we reconstruct using this as an input into the inversion, adding noise as we expect it to be. We then reconstruct as it would be seen by SeaSTAR, and that is what we see in the top right, where we reconstruct a lot of the structures. You can see even that is not perfect. I mean, they still, if we can push this performance a bit more, that will be will be better. And we are looking at that possibility of going to even finer resolution if we can. But the other 2 examples at the bottom are the sort of typical resolutions and uncertainty levels that are being proposed by some other concepts. And you can see that you lose that information, that spatial information, very, very quickly when you go away from the 1 kilometer and 0.1 meter per second. We have tested this also from aircraft. So for those who have not heard of OSCAR, OSCAR stands for Ocean Surface Current Airborne Radar, and it's an airborne demonstrator for SeaSTAR that was funded by ESA. So you can see it here under the belly of the aircraft. So bottom is the aircraft with the radome on its belly. And then within that radome, you have the system, as you can see, with its 3 3 different sort of look directions. And we have tested this. We flew this in May last year over Sea, just west of Brest in France. And it was a big campaign with lots of flights, both over some very energetic sort of tidal currents over the Ouessant Island, which you can just see there, just offshore from the coast of Brittany, and with very, very strong currents going through this sort of archipelago. The background image is again a Sentinel-2 image that shows just how the impact this is having on the optical signatures of the water. And we had many, of course, this was done in collaborations with many organizations who provided support in terms of validation and so on. I'm going to show you just very few results. I'll skip that because okay. So this is just one of those flights. So over the Ouessant Island, and shown at the top is the velocity. So you can see the color shows the magnitude of the current, and the little arrows show the direction. And on the bottom, you have the retrieved ocean surface wind, again, with colors and arrows. And at a resolution of 200 meters in this instance. And on the right-hand side, we have the equivalent kind of vectorial fields from models, high-resolution models. So we can see that we get, the structure looks right, the magnitudes as well. It's all on the same color scale. So that's very encouraging. So one thing that we spotted almost immediately is there are differences, of course, with the model kind of predicting the jets in the northern part of that of that sector to be much closer to the land than what we see in OSCAR. So we had to go for some additional kind of corroboration of what we saw which came in the form of a satellite image from Novasar-1. It's a UK satellite microwave radar that flew past almost like within an hour of our airborne acquisition, and shows very clearly that current gradient is where we detected it rather than where the model said. And then in the middle panel here, we have a comparison with some data we had from an X-band radar located on the island, which confirmed the position of the jet that we see in our data in the southern part. And then on the extreme right, we have the sort of one-to-one comparison of the magnitudes that you retrieve with the X-band system and with the Oscar system. And we get this very, very good comparison between the two. So very, very happy with these results, particularly in these very challenging environments. We have other results, but I haven't got really time to show this. If you want to see more about this, you must come to the UCM in Bucharest or attend, and then you'll see that we have some other results that are also very impressive. So this is about a second campaign that we flew in May this year, which I mentioned when I gave a similar talk earlier this year in the Wind and Current series. And at the time, none of that was confirmed. So all of this that we wanted to do, which we was still tentative at the time, has come to pass, has been funded, and has in fact happened. And the idea there was to take advantage of the SWAT-CalVal one-day repeat phase, which, as you know, happened earlier this year. And we identified this area just north in the Mediterranean, just north of Minorca, where SWAT was going to be flying every day, and where the BioSWAT project was planning to do many in situ maneuvers with ships and all sorts of deployments to provide some in situ validation. So we actually did manage to, it was a very, very short notice, but we still managed to commission the aircraft and everything, get the team out there and fly. And they flew this beautiful kind of rose pattern. We've had star patterns, now we have rose patterns north of Minorca, where we thought there may be an eddy. Of course, we didn't know that. As it turns out, the eddy was a little bit to the east, which is a shame. But nevertheless, we have the first results from Oscar for one of those tracks, which is what is shown in the top row on the right figure. Superposed with some low resolution SWOT data, because we're not actually allowed to show any high resolution SWOT data. So we have got access to some of it, but we're not allowed to show that until, I guess, next week, when all will be revealed and we can all share happily all we know about wonderful SWOT images. So really just to show, so these are the figure on the right are three snapshots on 3 successive days, showing Oscar at the top, on SWOT on the middle, and then just a picture of sea surface temperature in this case. And the conditions on those 3 days couldn't have been more different. They were absolutely incredible, just how dynamic the whole area has been. So it's still very preliminary. We haven't got the calibrated data from Oscar yet, but we have great hope of being able to retrieve some information about currents and winds that would be coincidence with SWOT at some stage. So it's a bit of a sort of a little bit of a what's the word? We try to tempt people to come and hear more. So if you want to know the end of that story, either come to the UCM or come to Ocean Science, when we hope to present some of that. So really, I want to come back to this uniqueness and complementarity point, which I raised earlier. And this is really what the timeline looks like. So SeaSTAR would be launched in a sort of 2031-32 timeframe, or shown here by this sort of big orange arrow. And you can see all the other missions that are expected to be flying at that time. So of course, is all the Sentinels, Sentinel 1, 2, 3, Sentinel 6, all of which will be still operational or indeed in extended life. And they are all relevant here because they are, you know, this complementarity between SeaSTAR and all of those images of SST, ocean color, SAR images, and altimetry, of course, fine scale altimetry from nadir SAR mode altimeters. And then, of course, there is the Copernicus expansion missions like Crystal and Simmer will give us additional capability, but in the high latitudes. And then we have the new generation of Sentinel, Sentinel-1 next generation, 2, 3, and then Sentinel-3 next generation topography, which people may or may not recall, has now been confirmed will be a wide swath altimeter. So that will be flying a SWAT type instrument pretty much at the same time as SeaSTAR. So there's huge opportunities there to do some analysis of looking at ageostrophic motions and sea surface height at the same time. And then in the middle of this, we have E10 Harmony. And as I mentioned, Harmony will be launched around about 2029, 2030. And there are some similarities between Harmony and SeaSTAR. And as I keep saying, to Paco's eternal chagrin, Harmony is the biggest threat to SeaSTAR because Harmony is also concerned with air-sea interactions. So, but our take is very much that Harmony and SeaSTAR are complementary. So Harmony, for those who do not know, and again, Paco will go through this in great detail when he gives his talk about Harmony. Harmony is a companion to Sentinel-1, and it is also doing these measurements of backscatter and interferometry, long track interferometry in different directions. So they will measure winds and currents as well at fine resolution. But of course, they're tied to the acquisition plans from Sentinel-1 and to its orbit. So there are many details we can go into about this, but by and large, Harmony cannot do the one-day revisit that we can do, and it's not sampling the global ocean margins in the way we do. So when you look at the coastal, at the masks, acquisition masks of the two missions, it is very clear how complementary the two missions are. And we are looking forward, both I and Paco are really trying to push to the idea that we should try and get SeaSTAR and Harmony to fly at the same time, because there would be great benefits to this happening. SeaSTAR would benefit from all the work Harmony has done in terms of calibration, validation, and so on, and building the science community as well. And then Harmony could actually benefit from SeaSTAR's finer temporal sampling, finer resolution, and reduced, lower uncertainties compared to what Harmony is doing to try and enhance its observation and understand a bit better what's in their data. So there's a great benefit. This is an incredibly sensitive topic, as you might imagine, and it has, it is going to be the most sensitive and most difficult aspect that we have to handle. But certainly from my perspective and from Paco's, there is no conflict. It's totally complementary. So that's my summary. So SeaSTAR is a science-driven mission with a solid science case. I hope I have managed to convince you of the need for the observations that we propose to take to deliver, and it's addressing a very broad number of scientific topics that talks to a very large community of oceanographers, but also scientists in Earth system and in climate sort of science. Of course, I have completely not mentioned the practical interest in SeaSTAR from having these type of observations, particularly in coastal zone and in marginal ice zones, where this type of information is hugely valuable for all sorts of practical applications and so on. So the societal benefits of the mission are really unquestionable. We think it is a quantum leap in knowledge for Earth observation and Earth science. I know it sounds a little grand, but it is. I really think that this would provide unprecedented capability and also sampling, seeing the dynamics at this very, very short, very, very frequent revisit is something we haven't been able to do until now. So it's a very demanding, has very demanding requirements. But it's a highly innovative concept. It would be the first instrument of its kind in space. It is challenging, but we are confident that European industry have got the know-how and the technology readiness to make this a viable concept for Earth Explorer 11. I think that's me done. So yeah, if you have any comments or anything like this, which we haven't, there's no time to cover today, or any questions you don't want to ask in public, and just email me. There's a little website for SeaSTAR with sort of the basics. It's a bit out of date, so it will need to be updated. But really, please consider coming to the UCM or attending the UCM. If you do, please register by 25th of September. The details of how to do that are shown there. And yes, it's important for the community to express their interest and support for the mission. And I'll stop here. So thank you.
Well, thank you so much, Christine. This was great. Questions from the audience. And as always, I really want to encourage early career people to speak up. While people are thinking of questions, let me ask about the satellite orbit. Are you planning this as a sun-synchronous orbit?
Yes, sorry, I didn't mention that. But yes, because we're essentially running 3 SARs radar instruments on the same platform, we have huge requirements for power. So yeah, sun-synchronous it's not even, at the moment, that's the only thing we can do. So yeah, sun-synchronous. And the orbit is something like 570 kilometers, if I remember correctly. Any other questions?
Well, I'll keep asking then, because then the other question that goes with the orbit is about tides and near inertial oscillations and what those might show up as in the region that you're looking at, and how you think you'll handle that. Yes,
the tides is something where we are aware that we are going to be aliasing those. That's clear. So we will, all of these data for SeaSTAR are not going to be the answer by themselves. Like, if you try to understand what's happening in terms of vertical processes as well, we cannot do it simply with SeaSTAR data. So SeaSTAR would be kind of providing additional information that you use in combination with other things. So particularly the role of models is really important here. So we will give snapshots of tides, but we will not necessarily we will not actually aim to do very much on tides, other than to provide snapshots that people who do tidal modeling may want to use together with sea level, sea surface height data to improve their models. So we have to be careful not to claim that we can do everything. Certainly, yeah, there are many even faster processes that we are not going to be able to observe, even with a one-day revisit.
Other questions?
It must have been crystal clear.
Tony Lee has his hand up. Let him go ahead.
Hi, Christine. Thank you very much for the comprehensive talk. Look forward to hearing more.
Yes, thanks for coming.
OSM. Yeah. So I have a question. Have you been engaging the Ocean Pacific Coastal Shelf Sea forecast community and the biology community to gather their support? And can they use the data, such high resolution data?
Yeah, so we have people on the mission advisory group who are members of those initiatives, and they are kind of providing the liaison with that. They are aware, because I have made sure that those initiatives are aware of this, and they will be sending representatives at the UCM. The biology community, again, it's been very hard actually to get them interested. It's new satellite missions is not perhaps everybody's top priority when it comes to how they spend their time. So we have some engagement, but there are many people who I think would benefit from this and are probably not aware of it. So we definitely need to make a lot more noise. And as I said before we started, we have been very busy the last few months to make sure we have concepts that actually are viable from a prospect of programmatic, so mainly particularly cost and feasibility, because those have always been the big hurdle for SeaSTAR until now. It's been this issue of, will this fit in the cost envelope for the program? And we have spent a lot of effort on that the last few months to make sure that that is the case. And we are confident that that is the case now. And ESA agrees that that is the case. So now is the stage where we do need to make more noise about the mission and make sure that everybody who is interested in this will is aware of the capabilities that we offer. I think one of the interesting things, I think we had this discussion last week, I think, as well. This issue of silos, scientific silos. We have the scientific community can be kind of focused very much on physical processes, but not so much be concerned about biological processes, and vice versa. And it's bridging those disciplinary barriers. Is quite challenging, actually. And then on top of that, we have the Earth observation kind of barrier, which also exists in some people's eyes. So yeah, there's a lot of work to do there.
That's right.
Thanks, Tony. I'll look forward to seeing you in Bucharest.
Yeah.
Eric Desaro is up next.
Yeah, hi. Could you describe the orbit in a little bit, the orbital coverage in a bit more detail? I didn't catch all the jargon. I'm sorry about that. Talk about silos there. Here we're talking about silos. That was my complaint.
Hang on, I'll just try and find that slide again. This one. Yeah. So we are aiming for one-day revisit and subdalian places. And we have this choice of 3 orbits because we have an altitude where we can, by changing the altitude ever so slightly, we can shift between 3 orbits. So the first example is a one-day exact repeat, which is the same that SWOT used during its Calval phase. I don't know if you're familiar with that, but we basically have a set of 15 or so revolutions per day over the same track, which is what's illustrated here on the bottom left. In our case, we have a swath of 100 kilometers or so. So you visit that exact swath every day for however long you like. Bearing in mind that there is a finite lifetime for the mission, of course. So you have to kind of decide, on scientific grounds what you want to do. So at some point we can then shift altitude slightly and go into a drifting orbit. So it's still 15 or so revolutions per day, but those tracks will shift around the orbit, around the planet slowly. And so you still achieve a one-day revisit, but only for a certain number of consecutive days. And then essentially those tracks will cover the whole Earth. And after 91 days or 271 days, you are back on the same track again. And then you just continue.
So there's a one-day revisit on a tracks which cover a very small fraction of the Earth.
Yes. So you still have only...
you can shift those around to your favorite places and somebody decides.
That's right. That's right. Yes.
Okay, cool. Thank you.
Okay, you're welcome.
Christine, does that mean that the one-day exact repeat can be moved around to sit in different spots?
So that's also an idea which we haven't explored very much, but the satellite has good capability. Yes, so we could go into a fixed 15, a fixed one day, and then go into drifting, and then come back into an exact repeat. So that is also possible. And all of this will be, elaborated further in the next phases. But in the first instance, the important thing was really to see anything that will impact the system, in terms of fuel consumption or sensitivity to any of these sort of altitude changes. But all this seems to be fine. So the tough bit's been done. Then now we have this flexibility. We'll have to decide how to use it to best effect. And we will need to do at some point some experiments also with some simulations, really, to see how we can optimize this kind of sampling to achieve as many of our aims as we can.
Other questions for Christine?
I'm just moving back to the UCM so that.
If I can, then can I ask about in situ validation? I guess what strikes me is that the 1 kilometer resolution is really high resolution compared with, say, what we get out of HFR at the moment. And so it seems like this is revolutionary, but also challenging to validate. I don't know what you're planning.
So HF radar is actually going to be our workhorse for validation. So there are systems that will do the 1 kilometer resolution, but on its own, it is indeed not going to be sufficient. So yeah, exactly. How do you validate something that doesn't have any comparisons? So yes, it is something that we'll have to develop, and to a certain extent, Harmony will have similar questions as well of how they are going to do the validation. So I expect that in the next few years there will be more development or more thoughts about these types of issues. To a certain extent, the wind is actually even worse because wind is even more variable. We think, particularly in coastal regions. So how do you validate winds? At the moment, there's very little information about coastal winds. Yeah, it's always, these new missions that always have this kind of challenge of how do you actually validate the measurements you have. The Oscar airborne data, we have validated those against ADCP and HF radar, and I think current meters in the past we have used as well. So it is possible to some extent to use a traditional means of doing these kinds of validations, but the spatial dimension is going to be more difficult, and that's really where we want to use these data in synergy with other data, with other high resolution data, also from SARS, but particularly from SST and Ocean Color, to try and give a sort of fuller picture of what's happening at the surface.
Well, are there any other questions then? If not, we're coming to the top of the hour, and we'll thank Christine for an amazing talk. I'll stop the recording, and thanks everyone.